Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to the next lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. In the previous class, in the immediately previous class, we have been looking at some examples of the fluorescence in the nanomaterials case, and I've shown this particular example of the carbon nanoparticles in that particular class. Let us continue with some more examples on this. So kindly have your attention on this particular slide, which is now shown for silver nanoparticles. Silver nanoparticles in this. So silver nanoparticles have been synthesized using certain kind of a method. The method here is controlled current coulometry. Do you need to know that? It is not necessary, important. But assume that yes, we know that there is made, but you can make by using different kinds of the control parameters. For example, the rotation rate. So in the coulometry, you are rotating stirring the solutions. That stirring rate you are looking at. Reaction time, how long that is given, and what is the excitation wavelength. So all of these parameters influence. So kindly have a look at the panel 1 on the left top, the spectra that are shown. This particular spectra are for those silver nanoparticles which synthesized at the following conditions. One is the stirring was done at 500 rpm and the excitation was done at 420 nanometers. So what are the variation for this? The variation is the reaction time, 35 second, this the bluish one, the 75 second, the reddish one, the 300 second, the green one, and the 600 darker purple or something. So you're going from 35 to 75 to 300 to 600. So what is happening? As you increase that reaction rate kind of a thing, and then the nanoparticles development is slowed down or less in intensity that you're getting. These are all the SPR bands from which you're getting your corresponding fluorescence emission. So the fluorescence emission is dependent on one of the reaction condition called the reaction time. Okay, let us look at the rate of the reaction in this. So you can see that. So see the right top panel, and here what is kept constant is reaction time is 75 seconds. Like here 75 is red one, you're picking up one of those, and then your RPM excitation is at 420 nanometer like earlier. Now you're changing the reaction rotation speed or the stirring speed, going from 500 to 1000 to 1500 to 2000 to 3000. That means 1:6 fold ratio of increase in the rotation for the thing. So the one which is the blue here and the red here, and so the rotation rates, the green one which is having, so you have the highest at the 1500. When you go beyond that is lowered, and below that is lower. So you can identify now from this plot what is the optimal rotation required. Here you can find out what is the optimal reaction time required. So all of these kinds of things. Now if you fix the reaction time, if you fix the rotation is 75 and 500, now what is the excitation effect? And that is seen on the left bottom in this particular one, the panel. So you have this at the 400, this at the 410, this at the 420, 430, 440. You can see the emission spectra is moving from somewhere around 510, 520 to almost 580, 590 kind of a situation in that. So you can make variety of fluorescence nanoparticles of the silver, and you can get variety of different kinds of tune. So these all depends on the conditions how you control. You can see that. Another example is shown for a 75 seconds with the 500 RPM, but different wavelengths of excitation. So with the different conditions. So you can always optimize all of these. So with the optimization, you can plan what kind of a nanoparticle, the reaction, synthesis, what level of time of reaction, what level of time of what level of the rotation, stirring, all these kinds of things, excitations. So I hope you understand this is a kind of an application. And then depending upon the type of nanoparticle that you have, further application can be planned. So this itself is an application of the fluorescence, and further these nanoparticles, silver nanoparticles, can be used for additional applications. Let's look at another example here on this. This is a composite formation, and one of the composite is zinc oxide, the other one is the glutathione based gold nanoparticle, and you can join them together as a composite as well. Now please look at the slide in the top left corner. Here there is some the egg yolk is being used, that is shown, and to this you add the zinc nitrate solution. Okay, so the zinc nitrate you stir, and the solution is taken and heated at 750 for 4 hours and gives a compound which is the zinc oxide nanoparticle. So this particular thing, zinc oxide nanoparticle, how do we know? By looking at the TEM spectra. So right now you don't need to worry that part, but though I have shown it here. Now on the other hand, parallelly, another reaction, you take auric chloride AuCl4 minus or HAuCl4, and then you need to reduce, because in this the HAuCl4 you have, so you have Au is in Au3 plus, so then you need to use a reducing agent. So this reducing agent here is the glutathione GSH, and that will give you Au0. So gold nanoparticle which are connected with the GSH or others, whatever the product of that. So that is where, so you have the glutathione, you have the auric chloride, and reaction at 90 degree 3 hours you getting, and you can see from the TEM. Now you don't mix the TEM micrographs, but you mix the materials. So you can mix this as well as this and reflux at 24 hours reflux, and then you get a different kind of a thing. So those are nothing but the zinc oxide coupled with the gold. So zinc oxide gold nanocomposite. So you can call this as A, Z and O. So this can be called as ZO, this is A, AU, the AZO. This is obviously a composite. This composite can help in a lot of applications. That's what we are looking at. First, before we go to that application, look at the how do you find this is ZO. The black one is just the simple. Kindly look at this particular panel A shown on this particular slide. For ZO, that you have the absorbance spectrum 376. For the AZO, there is this gold one at a little broad feature here as well as the 380. And if you have the glutathione bound nano cluster, this alone will show here. So this is a combination of this plus this. So you can see this part is coming, this part is coming, but slightly shifted with here, so that you have a composite. And since this is a fluorescence application, you can see the fluorescence, the spectra also. So this is a normalized emission which is shown. So you can see zinc oxide emission coming over here, and then gold clustered composite of the zinc oxide is coming over here, and then glutathione nanoparticles are coming here. So you have the spectra, the fluorescence spectra corresponding to the starting materials as well as the composite. Now let us look at some applications. This is a characterization. This is called characterization. Now the application is shown. Variety of applications are there if you go into this paper, but I picked up one example of the application which will differentiate between the single strand DNA versus the double strand DNA. That is the application. You can also look at other kinds of things. The sequence, what is the kind of a sequence? So is it a sequence dependent? Yes, that is also there, but I have not given that example here. But when you go into that paper, I suggest you that you need to you can look at those examples as well. Now example 1 in the A, in this one, A is the single strand, SS means single strand ctDNA, then you can see how there is a shift of the delta max by about 5 nanometers towards the blue side, you can see, and that itself is an indication for that one. And then the next one is for this AZO, that is gold containing zinc composite. There are two at the saturation. You incubate them and leave it for some period for saturation and then look at the spectra. And the corresponding spectra, if you look at here, this is for the simple that gold zinc oxide, and then when you mix the double stranded here, and when you mix the single strand here, double strand here. So from the shift of this particular position as well as their intensities change, because these are all normalized intensities, you can compare them directly. So you can see the shoulder, which is greater for the single strand, it became less for the double strand, and the position is also shifted. So this becomes a material which can be used to identify the single strand versus the double strand. If you have a small fragment which you synthesize, you can also check. You can have big ones, you can also check. As I said, this paper also deals with a few additional examples of that, which I am not taking in this particular thing. I hope you understand that. Let us look at maybe some more examples of this. Okay, here we have again a composite. The composite in the previous case, zinc oxide and the gold and combined together. Here we have an iron, gives the iron oxide by the hydrolysis, and the ligand will be captured, and the zinc and with the sulfide source will give you zinc sulfide, which is a quantum dot. Now you mix the two together, and that is what the composite is. Now let us look at the iron chloride with citrate at 200 will give you citrate bound, and then at this particular condition, so that it can also make the iron oxide, which is connected with the this citrate things. And this you can modify this carboxylate with this one, because you are going to do a reaction. This will become a easy eliminating group. That is why you are adding this one. Now on the left side, you make your zinc salt with the sodium sulfide, and then you can get, similarly you can do manganese also. So any one of these, so you can take, so that will become the amine terminal coming, because the cysteine has got the sulfur groups binding towards the zinc sulfide side, and the amine is protruding outside. Now you mix this with this one. So this amine will act as a nucleophile and knock on this and remove this one and connect it here. So you have an iron core particle and surrounded by this, the cadmium sulfide, the quantum dots. So you can visualize that as the iron core and quantum dots. This is greenish yellowish ones are the quantum dots, and the blackish whitish one is the iron oxide nanoparticle. Now you add application. Here what is the application that you are doing here is the lysozyme will get added up to this between these ones, and that fluorescence will change, and you can remove by some other processes, they remove the protein, add the protein, so you can get back to this. So this one you can see, these are from the A is the black one, which is the MNP with the quantum dots, the magnetic nanoparticle with quantum dots, and these made at the molecularly imprinting nanotechnology kind of a product that you have, and that has this one. And then to this you remove the lysozyme, you get the B, and you removing lysozyme, and then you get the simple quantum dots with MNPs. So you have the control spectra here. But here on the other hand, you take this MNP quantum dots with the MIP printing, that is this one, so that this kind of a thing, then you add your lysozyme. So you initially you have a fluorescence emission here, no lysozyme, then you add lysozyme 0.2 micromolar, 0.4 micromolar, 0.6 micromolar. You can see what is happening to this, the fluorescence is decreasing. So I am showing on the slide, so kindly have a look at it. So now if you plot these one, you can get the quantification of that. So therefore this imprinted kind of a technology that you are using, you are imprinting this lysozyme bound onto this particular magnetic nanoparticle coupled with this the quantum dots that you are looking at. So So a lot of other kinds of, if you do for other proteins like cytochrome C or bovine serum albumin or ovalbumin, any of these things, they don't show this kind of a the fluorescence quenching. So this is by the fluorescence quenching you can make. This is another application. So I have shown several applications of fluorescence with the FRET, with the direct fluorescence, and for the nanoparticles, nanomaterials in that. So we have looked at a variety of examples now on the fluorescence, okay, which are useful for the inorganic chemists, coordination chemists, bioorganic chemists, and the materials, nanochemistry, all of these. Now look at a little on the analytical applications of this. So the fluorescence spectral applications in analytical chemistry kind of thing. The examples I'm talking to you here are very mundane, routine kind of thing. You don't need to really much understand except for the following principle or phenomena, which I'm going to explain to you just in a while, but otherwise you can take, these are very straightforward kind of thing. We have some molecules here, the 8-hydroxyquinoline, alizarin, garnet, and flavanol, benzoin, etc. And when you see that, what you get a feel that they have some binding group, so therefore they can be good for complexing some metal ion, therefore you can look at the corresponding emission spectrum. So, and then quantification. So analytical application gives both the qualitative and quantitative kind of a analysis of that. Now, so this table will tell you how they have utilized in the literature aluminum 3+ with the alizarin absorption spectrum, emission. So you can use quite low the limit of detection. So these are not necessary to remember or mug anything, okay. And the fluoride can be detected by aluminum 3+ quantitatively up to 0.001 microgram per level, B4O7 2- benzoin. So what happens in all these cases? This metal ion will bind to that. This F-, this is with the so already this you bind with the aluminum and then attach, you add the iron as a fluoride, sorry. So you first take this one, attach with the aluminum 3+, make a complex of aluminum 3+ in the same solution, you don't need to isolate. Then to that you add your fluoride. Then you look at the changes in the fluorescence spectrum. So from that you can quantify that. So for example, here this particular thing, benzoin, this one, can be used to detect the B4O7 2-, B4O7 2- got the oxo surface. Oxo surface can interact with the hydroxyl group, and then therefore there is a change in the fluorescence spectrum. In all these cases, they bind to the species that you have, and as a result of that, you're getting your fluorescence emission change. So quantitation you can use. So extent of emission. So few other examples are also shown for lithium, for tin, for zinc, etc., etc. So variety of these things. Let me explain another arena where you can use analytical chemistry applications is the chemiluminescence. So in the chemiluminescence is that means there is no excitation. So this is there is some chemical process. So there is a chemical reaction occurring or chemical process occurring, and as a result of that, the excited state will give you emission. So that is what is chemiluminescence. So that is where chemiluminescence is that chemical reaction bringing the excitation, and then excitation will automatically come to the emission. So therefore that emission is called, instead of fluorescence you will call chemiluminescence. In the fluorescence you need excitation wavelength. Here you don't require excitation wavelength. Reaction itself brings the excited state. How? An example here you can see the A plus B gives a C in its excited state. That is why it's shown as a C star and D. The C star comes to the ground state and gives a light energy, and that's what it is. So there is no lambda excitation. Excitation here is basically a chemical reaction. Example, you can see in the air you have atmospheric ozones, oxides of nitrogen, sulfur oxides, sulfur compounds, variety of things are there. It's a very important reaction for atmospheric studies, pollutant studies. So nitric oxide is present, and that and the ozone together can provide, when they react at certain conditions, We don't need to read those conditions, but they are all given here. If when you have a time, you can read, that will tell you how exactly you need to do that. So you take them into a particular tube and then maintain a particular temperature, etc. Then you have this NO2, but NO2 in excited state will come. This excited state NO2 will relax back to the ground state NO2, and that gives the emission. This emission is measured. So extent of this emission, that is intensity, the luminescence intensity, is measured here. Okay, so you can also measure the NO2 directly. Here NO2 going to NO2. So NO2 initially you can break down to NO plus O by heating it at a high temperature, thermal decomposition, and then this NO can go through this kind of a reaction again. Not only oxides of nitrogen, ozone, you can also use the oxides of sulfur. For example, sulfur dioxide, which is present in the air. So that is one of the things that people look at. So how do you look at that? You reduce that by heating a combustion with the hydrogen. So you can burn that with the hydrogen. You will get initially a disulfur S2 in the excited state. In the excited state, S2 when comes to the ground state, you give a emission, then you can find. So this is the emission occurs at a particular kind of a wavelength. So you can measure. So this is not only for qualitative, they are done for the quantitative as well. So in all this, there is no external lambda excitation at all. It is only reaction, chemical reaction. There is no limit. There are a huge number of examples are there, hundreds, thousands of examples are there. So I will be covering a few. One another which is very commonly used for the chemiluminescence is that this kind of a group. So this kind of a group can react with the hydrogen peroxide in basic conditions, and then can result into some kind of a species like that. So you can follow the chemiluminescence. Here again there is no lambda excitation. So this particular compound, which is luminol, can be reacted with H2O2, can be reacted with O2, many oxidizing agents, hypochlorite, many things in presence of the base will give you this reaction, and this plus the emission. So this emission you measure, you can use that. So this kind of a reaction leading to the emission is a chemiluminescence. So luminol is widely used in forensic science to detect small amounts of blood. The iron in the hemoglobin catalyzes the reaction, and can also be used in another example which is shown here in the right bottom of this particular slide, using the hydrogen peroxide as the oxidant. As I said, you can use hypochlorite, you can use hydrogen peroxide, you can use oxygen, many kinds of oxidative products you can use, oxidative reagents you can use. Concentration can be gauged to down to 0.01 nanomolar, okay, and chromium 3 you can do for 0.5 nanomolar, and copper up to down to 1. So you can study for cobalt, you can study for chromium, you can study for copper, many things. So several cations. So therefore no problem. It's a very extensively used for inorganic pieces in all these. So hope you got some feel of the extent to which the fluorescence spectroscopy can be used. No limit, as you can notice that. So before I close this particular topic on the fluorescence spectroscopy, I would like to draw your attention to kindly do certain level of the practice. At the end of every topic, I have been giving these things with some clues and expecting that you sit down and work. And this is very simple to work if you really understood the principle. I am using only 10 to 15% of the time, and the rest of the time, maybe 75 to 85% of the time, I am using an examples in every topic. So therefore that their examples contains a lot of applications. Applications based on the inorganic chemistry, analytical chemistry, coordination chemistry, bioorganic chemistry, materials, nanosystems, nanocomposites. So all of these are being given for every topic. The topic previous for the absorption spectroscopy, the current topic which is the fluorescence spectroscopy, future topics also it will be the same kind of thing. So kindly have a look at this. So let me go through this in this particular exercise, and if there are some clues required, I will give you, and that so that you can work out. So what I want to do is I give you enough freedom to look for the data in the fluorescence data for any pH titration. So take that one, start analyzing, okay, and deduce the requisite parameters. So you make a plot out of that if the plot is not given. If the plot is given, use the same plot, and then you can try to deduce the pKa values, other things. Suppose in some cases the molecule can undergo different transitions, so you can get different pKa values, etc. So all this. So it's not that one example you take at least a few examples. In some of them there is only one, in some of them there will be 2, 3, etc. So all of that. So this one query I am putting it is not for one set of examples, one set of data, can be multiple data. So look at the other one. While pyrrole does not show much fluorescence or almost no fluorescence emission, the amino acid tryptophan shows high fluorescence. So first of all, you need to know what is a tryptophan. You can Google, you will get the structure. You already know also possibly. Has the benzene fused with this kind of a pyrrole kind of a ring, and I have already explained as a principle, when you have a fused these 5-membered heterocycles, then the fluorescence emission comes because of the effect of the pi to pi star is greater than n to pi star. I already explained to you. So you just think, etc., and then do that. There are several amino acids that they are naturally occurring 20 and 20 plus nowadays. So which of the amino acids exhibit fluorescence, and explain why. So I'm sure you understand, because the observable fluorescence will come only when you have like beyond 300 nanometers or so in the UV and beyond 400, 450 in the visible. So which of the things can give obviously aromatic ones. So you can pick up the aromatic ones and work out. They are already available, and you can Google get those things also. First you attempt, then you can look at that. Okay, look at another example. Pick up a fluorescence titration data for any ligand with metal ion titration from the literature, and explain the features and derive the ratio of the metal to ligand in the complex form. Also, I have shown already such examples in my lectures. Don't take the same things, please take new data from the literature. So what all you can get? You know the concentration or mole ratio on the x-axis. You can put the mole ratio on the x-axis, and mole ratio of the metal to the ligand or ligand to the metal, whatever you are doing, and the fluorescence intensity. So from that, so this is the kind of thing you can make your. I have already explained, and the examples are there. If not explained a direct example in the fluorescence spectroscopy, I would have explained under the absorption spectroscopy. It's one and the same. The methodology is one and the same. Only the one is the fluorescence spectrum intensity, other is a absorption spectral intensity. That's all the thing is. Discuss the criteria in the previous class. I have explained to you the fluorescence resonance energy transfer, and how donor acceptor the overlapping. So please look into those. So explain the following FRET based. I have already given large number of examples with the copper, example with the iron, quite a few things, cadmium, some things. I said that there are hundreds of examples that are available. There's another one which is for the anion. So it's already shown. You need to explain that, and very clear. In one case you have the FRET. In the other case, when it is bound to the sodium sulfate moiety is reacting, then this will go farther. Therefore, there is no FRET. Okay, also some other examples I mentioned here. Fetch fluorescence spectra data from the literature for gold nanoparticles acting as chemosensor. There are a large number of gold nanoparticles or gold nanoparticle coated compounds, if you want to call some kind of a composites, and they all are used for variety of chemosensing. So you can get easily and you can interpret. Okay, another example, explain how 8-hydroxyquinoline acts as a fluorescent sensor for lithium plus because of the chelation, complexation. Explain how benzoin acts as a fluorescent sensor, I explained earlier, for the B4O2 minus. So the oxo ions interacting with that through the charged dipole as well as a hydrogen bonding, etc. Address how chemiluminescence differs from fluorescence. In this lecture, I explained to you what is the chemofluorescence versus the fluorescence, chemiluminescence versus the fluorescence, by defining both of these with a clarity and upon comparing them. In one case you have excitation, in another case you have a chemical reaction. Chemical reaction producing excited state, that's what the difference is. I hope that I have covered overall total 4 lectures, starting from the very basic concepts and then going through variety of applications of the fluorescence. So I think we have to stop at that stage, and in this case we will stop at this. So with these 4 lectures, please do some practice on this, so that you appreciate the subject, its applications. It will be useful for simple researchers and master students, and even people who are working in the industries, developing some catalysts, developing some nanomaterials, looking at the nanomaterial things. So all can be benefited from this. Thank you very much.